the revision for the finite dimensional calculus is over, and now we are at a stage where we can go to the description of the extremization of functionals. So, let us now slowly start by introducing what is a functional. Okay. So, in my first lecture I had briefly said that functional is a function of a function, or in pure mathematical language, a functional is a map from the set of all functions. So, this is the set of all functions x to the set of real numbers, where this time my vector space is x comma the norm, where this particular norm is the function norm, which I am going to describe in a minute. So, this particular vector space is an infinite dimensional vector space, or I would say function space. Okay. So, before I move ahead, let me quickly give some examples, right. A simple, very simple example could be j of y, where y is a function of x, is the maximum of y evaluated for all values of x in R, right. So, we can see that the maximum of the function y of x will be a real number. So, this is a map from the set x to the set R, and hence a functional, right. So, let us now continue our description. Let us further say that S be a subset of this set of functions. So, S is a subset of x, right. So, let us further say then J has a local. So, note that my description of a local minima or local maxima, or in general local extrema, will follow in a parallel manner to the description of, like we did in the description of the finite dimensional calculus. So, continuing, let J has a local maxima, let J has a local maxima or a local minima, right, in S. Let J has a local maxima or local minima in S, and let y be a function in this subset of functions, in the subset space S of functions, if there exists an epsilon. So, I am trying to describe the definition of the local minima, the local maxima of this functional j. So, that can be done if there exists an epsilon positive such that j of y hat minus j of y is less than equal to 0, respectively for minima is greater than equal to 0 for all y inside this subset S, whenever I have that the norm of y hat minus y is less than epsilon, right. So, what I have just said is that suppose y hat is another function in this space of functions S, and it is in an epsilon neighborhood, right. What I have just described above is the space of all functions in the epsilon neighborhood, of y, right. All of these functions, they belong to the subset S. We call this y hat, since y hat is in the epsilon neighborhood of y, we call this y hat to be the perturbation of y, right. Y hat is the perturbation of y. Okay. If I can write y hat in the following manner, where y hat is y plus epsilon eta, right. So, all these definitions are equivalent. Y hat is in an epsilon neighborhood if y hat is a perturbation of y, if y hat can be written in the form of this following relation, y hat is equal to y plus epsilon eta, where I describe my functions eta to be the space of perturbation, to be coming from the space of perturbation functions with zeros at the end points, right. So, I describe my epsilon neighborhood set, I describe my epsilon neighborhood set of, well, of course, epsilon neighborhood of within the epsilon neighborhood of the function y. So, I describe this epsilon neighborhood set as h epsilon to be the set of all functions eta in x such that y plus epsilon eta is in this set S, right. So, this is my set of all perturbation functions. I call this as my perturbation set, right. Okay. And I can always make epsilon to be arbitrarily small, right, arbitrarily small. So, I can always modulate my perturbation such that it is closer or farther away from the function under consideration, right. So, now with all this definition, this basic definition of a functional, let us start describing the result that is the goal of this lecture, right. So, what we have is the following. So, I am going to describe the simplest possible variational problem, that is the fixed endpoint variational problem, right. So, my boundary condition is such that the values are fixed at the boundaries. So, let me say that my function space x is the space of all continuously differentiable functions up to second order inside the interval x 0 to x 1, right, which is the space of all, as I said just now, the space of all functions from x 0 to x 1 with continuous second derivative, So, let further say that J is a functional from this space of functions C 2 x 0 x 1 to R. So, J be a functional such that J of y is from x naught to x 1 f of x comma y prime dx, right, where f has continuous second partial derivatives with respect to all the variables involved in the argument of this function with respect to x, y, y prime, right. Or I say that J has a local extrema in S, where my subset S is the set of all functions which are second order continuously differentiable in the interval x 0 to x 1, such that the endpoints of those functions are fixed, y of x naught is y naught and y of x 1 is y 1. Okay. So, this is my set S. So, from now on, whenever I describe the set S, it is identical to this particular description of the set. Now, similarly, we can describe my perturbation set H. So, I have dropped my subscript epsilon. So, my perturbation set H is the set of all functions eta, again second order differentiable, such that this time the perturbations vanish at the end point. Okay. So, then we can further assume without loss of generality that suppose x has a local maxima at y, sorry not x but j, we are talking about the functional j. So, j has a local maxima at, well, the local maxima has to come from the set S if for all epsilon positive local maxima, well, what I meant to say here is local maxima at y in S, right. If for all epsilon positive, I have the following inequality which holds. So, j of y hat minus j of y must be less than equal to 0 for all y hat in S, right. So, what I am saying is, if I have to draw this all these statements pictorically, I am talking about a function which vanishes from, well, sorry, I am talking about a function starting from x naught y naught to x 1 y 1 and which can be perturbed using our perturbation function eta. So, this is my y hat which is y plus epsilon eta. Well, so let me just be a slightly more clearer. So, this is y plus epsilon eta and this particular function is y, right. So, suppose we have a local maxima at y, then it must be that for all epsilon all y hat in the epsilon neighborhood, we must satisfy this inequality, right, for all y hat such that, as I said, y hat lies in the epsilon neighborhood of y, right. And so that is the definition of the local maxima. So, now let us expand our function f using Taylor series expansion. So, if we use Taylor series, let us expand our integrand. If we go back to our previous slide, I am, well, not even the previous slide, the one before this, well, we have introduced, let us see where is it, well, I am talking about this particular definition of the functional with the integrand f, right. So, let us expand this integrand f of x comma y prime using the Taylor series. Let us say we are expanding at f of x comma y hat prime, where y hat is the perturbation of y. Okay. So, using Taylor series, I have that this is equal to f of x comma y prime plus epsilon of eta del f del y plus eta prime del f del y prime plus order epsilon square, right. We see that this particular function, I have expanded this integrand up to the first order terms and kept the higher order terms in this quantity here. Okay. So, then once the integrand has been expanded using Taylor series, I can correspondingly define the functional containing this integrand. So, what I have is j at y hat minus j at y will be the integral at f of x comma y hat prime minus integral f at x comma y prime, right. Well, which means substituting these values and then taking the necessary cancellations, we see that this particular difference is the integral. So, these are along the endpoints x 0 and x 1. This particular integral is integral from x 0 to x 1, x 0 to x 1 epsilon eta del f del y plus eta prime del f del y prime dx, right. So, this is the quantity that remains after we do the necessary cancellations, right, and of course, plus order epsilon square or higher order terms. We see that we call this this entire expression as epsilon times the variation of j, right. So, the variation of j is this following integration of this following term, right. So, what I said is where my variation of j of y is the following integral del f del y prime dx. Okay. So, or this is my first variation of j. So far we have come to a point where we have described the first variation of the functional j. Notice that if my perturbation is eta and I replace eta by minus eta, then minus eta also is in the perturbation set, and my variation of the functional at eta comma y satisfies this following equality is negative of the variation at negative eta comma y. We can just plug in the value of negative eta and see that this relation holds, right. Okay. So, then let us now, well, we have to start naming some equations with some numbers. Let us call this expression as 1 and let us call this particular expression that I have this boxed expression as my expression 2. Okay. So, then I see from 1 that for small, well, let us go back to that expression. So, we see that from 1 we see that if epsilon is small enough, then the sign of this difference, whether this sign is positive or negative, is completely controlled by this first term, because higher order terms will have magnitude which are even smaller than the first term, right. So, what I just said is the following. We see that for in 1 for small quantity epsilon, the sign of j of y hat minus j of y is determined, j of y hat minus j of y is determined by the sign of delta of j of eta comma y, right. Now, well, we want that this particular variation should be sign independent, should not depend on epsilon, and that is only possible when this variation is 0, right, for all set of all perturbations, right. Otherwise, if the variation is sign dependent, we will not be able to find the extremal, right. Again, a result which follows in parallel to our finite dimensional calculus case, right. Okay. So far we have arrived at a point that to find the extremal, we must have the first variation must be equal to 0. I call this as the necessary condition for finding the extremal, necessary condition for local max or local min. I am talking about max at this stage, well the similar argument holds for local min as well, right. And this is, so as I said, this is an analogous analog case of grad f is equal to 0, that we did in the finite dimensional calculus case. Okay. So, then what we have is the following. From 2 that we, from the expression 2, again let us recall, the expression 2 is this particular quantity described in terms of these derivatives. Now, what I want to do is I want to change this second term using integration by parts, so that even this term has a particular factor eta, and I want to pull out this perturbation function eta out of this integral or this integrand, and show some results which is independent of this perturbation function eta. Okay. So, then from 2 what we have, let us look at this second term, as I just said, integral from x 0 to x 1 eta prime of del f del y prime dx, right. If we use integration by parts by saying that, let us say this is my first function, this is my second function, we use integration by parts to arrive at the fact that this is eta times del f del y prime from x 0 to x 1 minus integral from x 0 to x 1 eta d dx of del y prime dx, right. Now, we also know that the perturbation functions eta are such that they vanish at the boundary. So, which means that this first term is going to be 0, it vanishes at the boundary, and we arrive that this particular quantity is the negative of this quantity. So, which means let me call this as 2 prime. So, from 2 and 2 prime I arrive at the fact that my first variation of the functional delta j of eta comma y is integral from x 0 to x 1 times eta of del f del y minus d dx of del f del y prime dx, right. So, we have, using integration by parts, we have now been able to come to a point where my integrand has a common factor of eta, and we know that for the extremal this first variation must be 0, right. So, let me call this result as 3. Now, intuitively all the students can see that what we are trying to do is we are trying to figure out a condition for the existence of the extremal value y, right, and we have found an integral condition, and from here what we will show that since this holds for all for any arbitrary eta, this must be true for the case when only when this particular integrand inside this bracket is 0, right. So, the integral being 0 leads to the fact that this quantity inside this bracket must be equal to 0, and that is our goal, right. So, as I just said that the next thing that we are trying to show is, let me call this quantity by E, right. So, what I said is I define my E from x 0 to x 1, E from x 0 to x 1 to R by E is equal to del f del y minus del x del f del y prime, right. So, this is the quantity I described by E. So, E is the function as follows. So, then my 3 I can write 3 in a very shorthand notation. My 3 is the inner product, where the inner product is defined with respect to this integral. It is the inner product of eta with respect to E, and for extremal. So, as I just said, this is the inner product of eta with respect to E is defined with respect to this integral, right, and for extremal this must be equal to 0 for extremal. Okay. Okay. So, then let us continue. So, what now I am going to show from this point onwards, that this integral being 0 will lead to the fact that E must be equal to 0, right. So, for that I need to show two small results. So, the idea, before I move on further, let me just state the basic idea here. To show that this function E is equal to 0, we will show by contradiction. We will assume that, let us say E is non-zero, although the integral is 0, and we will arrive at a particular contradiction, namely we will figure out an eta which is a perturbation function which is non-zero, and that perturbation leads to a contradiction. So, the goal is to find a particular perturbation eta which leads to our the proving of the result via contradiction. Okay.